going back over K, before we progress into reaction quotient and then Le Chatelier, yes, you have to be able to interpret the magnitude of K. K is greater than 1, K is less than 1, K is equal to 1. And if K is very, very large, usually this is the one that is very important because it changes the system to being basically an irreversible reaction where it goes directly to completion. So you would treat it not like an equilibrium state, you would treat it like a regular reaction and do regular stoic with it and so forth. Now, remembering that K is greater than 1, the products are favored. This is how you would state that the product predominates at equilibrium means the equilibrium lies to the right or on the product side. If we're looking at K is less than 1, the reactants are favored and they predominate at equilibrium. There's more reactants than there are product at equilibrium. So we say it lies to the left or lies on the reactant side. When we use the phrase where is the equilibrium position where it lies, that is referring to the actual equilibrium position. You don't say that when you're talking Le Chatelier's or which way that the reaction is proceeding. They're different phrasing. So when you're saying the equilibrium position lies on the right or the left or the reactants or the products, you're really referring to the system is at equilibrium, it hasn't been disturbed, and you're referring to, of course, K there. Now this one, like I said, is very important. The K value is much larger than 1. I mean, like the 2.5 times 10 to the 7 problem that we just did, that would be like a completion reaction. It is so large. It's essentially going to completion. We wouldn't treat it as an equilibrium problem anymore or a reversible reaction. We would just, all of the reactants are turned into products. And like I said, then you would use regular stoic with it, not the equilibrium calculations that you're going to see later on. So much, much larger, it goes to completion. You need to rethink that and go, okay, this is not at equilibrium really, so let me treat it like a normal reaction. If it's very, very small, like 10 to the minus 12, 10 to the minus, 15, very small number, really it never gets started. So minute in amount that we would say the reaction never began. So if equilibrium lies to the right, the value of K must be
greater than 1.
Greater than 1, because it's to the product side, lies on the product side. If equilibrium lies to the left, the value of K is less than 1. Now let's go ahead and remember as to why this is. You get the generalized law of mass action, which technically would be all of their concentrations raised to the powers of the coefficients in the balanced reaction. But generally you could write it like this. K is usually the products over the reactants. The product concentrations or the product partial pressures over the reactants concentrations or reactants partial pressures. So if it lies to the right, that means the numerator is bigger. So that's why K is going to end up being 1. If it lies to the left, that means the denominator is greater. It is a greater amount. So that's why when you do the division, the K is less than 1. You got to start really thinking about it in terms of the mathematical ratio. Okay, so now we're going to look at systems that aren't at equilibrium. And we're going to define it in terms of the reaction quotient, or Q. K and Q are equal to the same expression. We're going to use that law of mass action expression in order to calculate Q. And the Q values are when your concentrations are not at equilibrium. They can be initial concentrations or they can be concentrations after a disturbance to the system. And then we're going to go through like if Q is greater than K, Q is less than K, Q is equal to K, of course, what those mean. So these are the kind of learning targets for this section. So reactants and products are not at equilibrium concentrations. We use the calculation of the law of mass action equation when all of them are non-zero. Okay, they have to be non-zero because you try to plug them into the equation. If you have a 0, multiplying by 0 on the top will give you 0. If you put 0 on the bottom, multiplying by 0 on the bottom gives you undefined. So that's why you have to have them all as non-zero values in order to calculate the reaction quotient. If one of them is non-zero, you pretty much can tell which way it's going to proceed in order to establish equilibrium anyways. So we're going to show you how to do that also. But we only use and calculate Q when we have all non-zero values. Okay, so basically here, this is what we're looking at to calculate Q. Instead of it being K, you basically just change this to Q. You're going to put in all the initials or the non-equilibrium concentrations, and you're going to crank out and calculate the number. The number Q then will be compared to the original K value at equilibrium, and we're going to be able to decide which way the reaction will proceed in order to establish equilibrium, or re-establish equilibrium if it was from a disturbed, the equilibrium was disturbed by some kind of stress. But it's basically the same law of mass action equation. The only difference is now we have Q here, and we're getting a non-equilibrium value to compare to the equilibrium K constant. Any questions? Same calculations, same formula, just getting a different number and comparing it to the K. All right, so if K equals Q, the system is at equilibrium. And I like this diagram because it shows you kind of in bar graphs. Q and K are the same, so you're right at equilibrium. You have the same speed, reactants making products, products making reactants. You have the same constant concentrations, so you are at equilibrium. Let's look at different scenarios though when you're not. So if Q is greater than K, there's too much product, and equilibrium shifts to the left, goes towards the reactants to reestablish that ratio K value. Now this is another way to write it, which will help point you in the right direction. If you write the KQ thing alphabetically, like you put K over here, K is less than Q like so, write it that direction. It does the pointing for you. It's going to proceed towards the reactants. The less than sign points towards the reactants for you. So if you write K first and then Q, it will designate which way it is going to proceed to establish equilibrium. Make sense? So you can use that little trick, but you have to write K first. To write it alphabetically, K comes before Q, and you put the greater than less than sign there, it's going to point the direction of the way it's going to proceed. Consuming products and forming reactants until equilibrium is achieved. So the opposite, of course, is true. K is greater than Q, right? K is greater than Q. Now it's pointing this direction, right? So it's going to proceed towards the products. Has too many reactants, it's going to proceed towards the products to get back to equilibrium. So consuming reactants and forming products to attain equilibrium. Once again, this trick only works if you write K first, then Q, and then you insert the sign between them. Now for the concept check. And I want you to really think about this in terms of what we just talked about between K and Q. We have in a reaction up here, the water vapor plus the carbon monoxide giving you hydrogen gas and carbon dioxide. You add more water to the flask. Is K going to be greater than Q, less than Q, or equal to Q? And I want you to tell me which way it's going to proceed. So go ahead and talk real quick to your group or people around you and try to come up with answer there. Is Q less than K? Does most of you agree on that one? No. Yes, okay, we will say yes. Q is less than K. So which way is it going to proceed? The right. Yes, it should proceed towards the products and make more products. Remember, you can use the trick where you write K first. So yes, it will go and point this direction towards the products. So it's going to make more products towards the products. However, I want you to all reframe frame this and look at it from the mathematical standpoint. Discussing with some, K equals products over reactants. This gives you your equilibrium number, your equilibrium ratio. Whereas Q, of course, is also the products over reactants, but this is the non-equilibrium number. Now, in this case, we had a system at equilibrium, but we're disturbing it and stressing it and adding in water. So where are we adding? We're adding to the denominator. We're adding more into the reactants. So that, when divided by the original product number, means Q is going to be a smaller number than the original K. So think about it in terms of the math here. So you can be like, oh yeah, that's why Q is less than K. That's why it's going to proceed towards the products. Question?
Is PNR used in polarity?
Well, these, remember, K does not have units because the concentrations all cancel each other out. Yes.
So the PNR is.
Yes, this is my generalized, compiling of the law of mass action equation into simple terms. We have all the concentrations on the products raised to the power of their coefficients over the concentration of the reactants raised to the power of their coefficients. But in general, when I'm just trying to think math terms, oh, I'm increasing the denominator here. So it doesn't really matter what the numbers are. If I can increase the denominator, that makes the Q value smaller. Right? So conceptually, these are really good multiple choice type questions because you don't have numbers. You have to think conceptually about it. Now, the next part. How does the concentration of each chemical compare to its original concentration? So did it increase or decrease, basically, in comparison to its original concentration? So talk it out. We'll come back in a minute. All right, so we're going to, obviously, the original problem, we added in water, right? So adding this in means it's going to increase in concentration. That's a given. We added more in, it's increasing in concentration. Which way is the reaction proceeding? Towards the products. So we're going towards the products, we're making more products, so what should be happening to the products? They should both be increasing in their concentration. Now, we didn't add in any more CO though, but in order to keep going till the reaction gets back to that original K ratio, what's going to happen to the CO? It's going to be consumed. So this one's going to decrease in its compared to its original concentration. Now remember, the reaction is going to keep proceeding this direction until it gets back to the K number. Now, the products and the reactants concentrations are not going to be the same as they were before we disturbed it. But they are going to keep going back and forth till they get to that same ratio of the products over the reactants. So they won't be the same exact numbers that they once were, but they will keep going until they get back to that ratio K value.
All the concentrations are increasing except the other reactant.
Well, because that other reactant wasn't added in and it starts to get consumed. So it's going to keep going to the right and it's going to consume your CO, but because we added in more H2O, that's going to help balance out that number, the reactant number on the bottom. Remember, we have our K equals P over R, so the CO number goes down, but we added in more water, so those two together will balance out to getting us back to this original, it's not going to be the exact same R number, but neither are the products. These products, they're increasing, so they're not going to be the exact same product number that they were before. But when you do the division here, it's going to give you that same K number. Once it gets back to the equilibrium concentrations, it will divide out and give you that same ratio number. But the products and the reactants will be at different concentrations than they were originally at. Okay? Let's take a look at the next example. Now we're looking at adding in the H2. The only thing that's different in this one is we're adding in H2, which happens to be product. So in that case, we're adding in product. Let's write it this way. Is K going to be less than or greater than Q? Less than Q, right? So which way should it proceed? Towards the reactants. Very good. Towards the reactants. Now, if you add in more H2, what should happen here? We're adding an H2, so what should it do in compared to its original concentration? It should increase. Now, what's going to get consumed over here? CO2 gets consumed, so its number is going to start to go down compared to its original concentration. Depending on the equilibrium position, it might not be a whole lot of difference, but a little bit. And what happens to our CO and our water vapor over here? These will both start to increase because you're making more reactants. Once again, it goes back to that idea that concentrations adjust, getting back to that K ratio value, that K value ratio of products over reactants. These numbers, like this number here and this number here, is going to be different now, but when you divide it out, it's going to give us that original K ratio number. Okay? Now, this was a good prelude to getting to Le Chatelier's principle, because basically Le Chatelier's principle, you're disturbing a system at equilibrium. So you're changing the concentrations to non-equilibrium concentrations, or changing the situation to non-equilibrium conditions, so it's going to have to adjust. So now we're going to start looking at it from Le Chatelier's principle. We're going to look at not only changing the amounts or the concentrations or partial pressures, we're also going to look at how temperature changes affect and pressure changes affect a system at equilibrium. So these are the kind of the concepts here that roll into Le Chatelier's principle. Now, the system at equilibrium is disturbed either by a change in temperature, pressure, or concentration of one of the components. Now, concentration also could be a partial pressure of one of the gas components, because we can measure like the amounts by its partial pressure. And the system will shift its equilibrium position to counteract the effect of the disturbance. Once again, it's going to shift or proceed in a direction to reestablish that K value. For the ones when we change the temperature, our K value is actually going to change. That's the only time the K value number will actually be different. But for concentration and pressure situations, those ones will go back to their original K ratio value. Let's take a look at the animation real quick. Okay, so looking at that, we're going to also discuss the Haber process in more detail, because that one's very important for our agriculture. But showing you there some of the different ways that Le Chatelier's principle is manipulated and can be looked at on the molecular level from the animation. So first we're going to look at concentration changes. And remember, concentration can also be partial pressure changes, because we can measure the concentration of the gas based off of its partial pressure. The system will proceed to the opposite side from where the component was added. So we added to the reactants, it shifted towards the products, or proceeded towards the products. We add to the products, it's going to shift towards the reactants, the opposite side. That's adding. Removing has the opposite effect. If you remove a product, it's going to proceed towards the product side to replace the product that's been removed. Or if you remove a reactant, it will proceed towards the reactants in order to make that reactant where that has been removed as well. Because the Le Chatelier principle questions a lot of times come in free response, where you have to explain and you have to state it with the correct terminology. So when adding gaseous or aqueous reactants, reactants proceed to the right towards the products is the actual correct phrasing. Now, if you said it shifted to the right towards the products, I believe they will still give you credit, but we've been told to stay away from the word shift, although it does mean the same thing. So that would be, one way to state it. When adding gaseous or aqueous products, reactions proceed left towards the reactants. Once again, correct faith, you're telling me the direction, where it's going. That's kind of how, when you're explaining too, explaining something like this, where you would say, if we're adding in gaseous reactants, That means that we're adding to the, denominator of the Q equation, so Q is going to become less. That's why it will proceed towards the right. So you reference that Q reaction quotient equation in order to give your reason, because it'll be which way is it going to shift, which way is going to proceed, and explain why. That's typically how these are worded in the free response. So for that case, when adding a gaseous product or aqueous product, adding in the product is going to increase the numerator of the reaction quotient, therefore Q will be greater than K, and then you can say it will proceed towards the reactants. So you can give your explanation that way. So just from removing gaseous or aqueous reactants, reactions proceed to the left towards the reactants. And when removing the gaseous or aqueous products, reactions proceed to the right towards the products. Just getting the correct phrasing in there. Yes, I mean, if you put the word shift, I don't think that they'll mark it wrong, but we would like you to phrase it this way. We've been told that this is the better way to phrase the answers. Now what I'd like you to do is look at this particular example and tell me which way it's going to proceed. You don't have to write out the full sentence just like before. I put in arrows here as to which way that it will go in order to reestablish equilibrium. Okay, so we add in nitrogen. Which way should it proceed? Towards the products to the right. Like I said, I put arrows in myself. But you would say, if you were answering for your response question, you would put it in a complete sentence. So adding in ammonia is going to proceed towards the reactants, that direction. Removing nitrogen, which way should it proceed? Towards the reactants, and removing hydrogen, which is also a reactant, is going to proceed towards the reactants. Very good. Now let's talk about endo and exothermic reactions, because you need to be able to identify them. Where is the heat before you can decide on a change in temperature is going to affect the system. So recalling that endothermic heat or energy is going to be considered a reactant, and it's going to be on the left side of the arrow. In an exothermic, heat or energy will be a product, will be on the right hand side of the arrow. Don't forget, they will normally tell you either by indicating to you by putting it in the balanced reaction itself, or they'll give you the delta H value. So you need to know that delta H positive, of course, is indicating endothermic. Delta H negative is going to be indicating exothermic. We have to know this before we can decide, adding in heat or temperature, which way it will proceed. Now we know that temperature affects the K value. It will change the K value, but why? When temperature increases, the forward and reverse rates both increase. If you think about collision theory, if you're increasing the temperature, all of the average kinetic energy of the particles is higher, and then they're all moving faster. But the thing is, it's not always equal. One of them is going to be greater than the other. So one increases more than the other, and this is a kinetics thing. We're going to do an entire unit on kinetics. So this is how it works. The endo reaction, where you're adding in heat, you are adding in an actual reactant. The temperature is the heat. On the left side, it's going to, of course, proceed towards the right to make more products. But in doing so, the collisions are, there are probably going to be more of them and so forth. It's actually going to alter the amounts at the end. So we're going to get a new K value. And it's going to create more of a top number, more of the product number. Okay, so that K equals P over R. This number is going to increase because the temperature is going to make more products, and it's going to alter your ratio. Exothermic, the reverse rate is higher, more reactants made, and of course if you're making more reactants, then down here our denominator part is going to increase, so K should decrease when you add in heat to an exothermic reaction. The reverse is also true. If you're removing temperature, taking away temperature from an endothermic reaction is going to proceed towards the reactants. K should decrease. If you remove heat from an exothermic, it's going to increase the forward reaction, making more product, so therefore K should increase. Any questions? Alright, so let's take a look here. Basically, it's the same idea in terms of concentration or partial pressure. When you add to one side, it goes to the opposite side. And if you remove from a side, it's going to go to the side that it was removed from. So heat kind of follows the same idea of principles as concentration or pressure, partial pressure of the gases. However, do remember though that K changes. That's the only time that the K number, the K ratio is going to change, is when you change temperature. Doesn't matter for anything else, not for changing the pressure, not for changing the concentrations, adding and removing things. The only time the K value, the K ratio itself changes is with temperature. Alright, so taking a look here at our example, where is this endo or exo? Endo, because heat is part of the reactants here. Good. So, increase in temperature means it's going to proceed towards the products, to the right there. A decrease in temperature towards the reactants. Now, the effect on K for increasing the temperature made more what? Products, so therefore the K number should get larger. Good. And then of course if we're going towards the reactants and we've added in temperature or heat and we've made more reactants, the K number should get smaller, lower. Very good. Last one here is the pressure changes. You must look at the number of gaseous moles, because remember gas is the only thing that's going to cause pressure. So we're going to be counting the number of moles of gas. You're going to do this based on the balanced reactions coefficients. Increasing pressure proceeds to the side with the least or fewer number of gaseous moles. Decreasing pressure proceeds to the side with the higher number of gaseous moles. Because remember, it's going back to reestablishing the same pressure that it was at equilibrium. Now, there's a couple added extra little tricks here for the pressure stuff. Changing the volume of the container will affect the pressure. We know this because of Boyle's law. So they can phrase a pressure question by saying they're going to increase or decrease the volume of the container. And if you remember that we have P1 V1 equals P2 V2, you can always figure out, is the pressure going to increase or decrease? If you increase the volume, the pressure should decrease. Still go to the side with more or higher amounts of gaseous moles. If you decrease the volume, pressure should increase, and therefore you're going to go to the side. It's going to proceed to the side that has fewer or the least number of gaseous moles. There is one more added trick to this, where they throw this in for AP. They could add in an inert gas, which would be like a noble gas. What does the word inert mean? Non-reactive. So it's not going to react with anything in the equilibrium system. These gases, noble gases like helium and argon and neon, they're not going to actually react with anything. So there will be no effect on the equilibrium position at all. The only thing that will happen to the system when you add in an inert gas is it will increase the overall pressure of the system, but it doesn't change the equilibrium of the reaction involved. But they love to throw that one in as a trick. So adding in an inert gas is not going to react with anything. It's not going to change the equilibrium position. The only thing you could say that it would change would be the overall pressure in the container. So once you're done with this, you can take a look at the example problem and decide which way it will proceed. First thing you should do though is what? count your gaseous moles on both sides of the arrow. That should be step 1. Alright, so let's take a look here. Pressure, of course, look at the number of gaseous moles here. Let's count them. How many moles on our reactant side? 4 moles. So how many over here? 2 moles. First thing you should do before beginning. So if we increase the pressure, which way will it proceed? Towards the products. Very good. How about a decrease in volume? Decrease in volume means increase in pressure, so therefore also to the right towards the products. How about adding in neon? That's an inert gas, so that should be a no change. Up. Well, we will go over here to decreasing pressure, goes to the side with more moles. So it will go to the product side, to the reactant side, towards the reactants where there's 4 moles of gas, the larger number of moles of gas. Increase in volume means what in terms of pressure? Decrease in pressure, so it's going to go to the side with also more moles of gas. And once again, adding in the neon should be a no change. It's not going to affect the equilibrium position. All it's going to do is add more pressure to the system. Because the neon is not going to react with any of our components up here. It's just going to float around and bump into it. Alright, here is the Haber process, where it's the nitrogen plus hydrogen giving us ammonia. And the only reason why I keep hitting back to this is because this is a relevant example of how they use Le Chatelier's principle to manipulate equilibrium and produce the ammonia. So as you can see that in the diagram, there's lots of stuff going on. They do have the catalyst beds where they use the iron catalyst to get it going. Alright, so adding in, once again, then of course they manipulate the heat in order to maximize the output. And it goes through heat exchangers. And over here on the right showing the condenser where eventually they'll cool it down so that you can get the liquid ammonia out as a product. But it's needed for agriculture because it's added to fertilizer. Of course, agriculture is needed in order to produce food for the many people that are in the world. So ammonia-based fertilizers obviously are very important. This is a big industry. This is a classic, relevant example of how the equilibrium equation here is manipulated using Le Chatelier's principle to get the maximum output of the product, in this case, the desired product being ammonia. Now the next picture is the diagram that's in your book. It's a little bit bigger, you can see a little bit better. But same idea, the incoming gases, they go through heat exchangers. Over here is the catalyst, and eventually goes down into the condenser and becomes liquefied ammonia, manipulated at certain temperatures and pressures. They said in the video. In the video, the pressure was about 200 atm and about 450 degrees Celsius is the one where it maximizes output. Here in this particular graph, it's showing 400 degrees Celsius and 500 atm would get you 60.6%. However, I'm sure in terms of maintaining this high pressure here is probably difficult. So they were saying more like 450 and 200, and 450 are the more optimal. But if you look at that, that's still only about 27.4% ammonia being produced. So although it would be way more efficient than not manipulating those factors. All right, last but not least, catalysts lower the activation energy of a reaction. But if you add a catalyst to an equilibrium system, it's going to lower it for both directions, the forward and the reverse. So it's basically going to speed up the reaction in both directions. Doesn't affect the equilibrium position. Because it's speeding it up in both directions, it's just making it get to equilibrium faster. So the other added trick besides adding in an inert gas would be to say they're adding in a catalyst. Catalysts obviously don't affect the equilibrium position, just make them establish equilibrium faster. So therefore, it's going to be a no change. No change. So when one uses a catalyst, equilibrium is achieved faster, but the equilibrium composition remains the same. So you would put no change or remains the same as your answer whenever they ask for adding in a catalyst. Any questions?